The California Energy Commission funded field demonstrations of this technology in 3 real California homes in 2024. The results, published in the Commission's official research program documentation, confirmed cooling energy reductions of 10 to 41%. No solar panels, no geothermal system, no new mechanical equipment of any kind. A panel installed on interior walls like standard drywall. The panel contains wax. The wax melts during the day, absorbing heat that would otherwise raise the room temperature and trigger the air conditioner. The wax re-solidifies overnight, resetting for the following day. The panel costs $60 per sheet at current retail pricing. Yet, fewer than 1% of American homes have a single sheet installed. By the end of this video, you will understand exactly why and what it would take to change that. The engineer who first proved that a phase change material could replace a mechanical cooling system in a real occupied building was a Hungarian-American physicist who spent the 1940s trying to convince the American construction industry that wax was a more intelligent building material than fiberglass. Maria Telkes was born in Budapest in 1900 and trained as a physical chemist before emigrating to the United States in 1925. She joined the MIT Solar Energy Conversion Project in 1939 and spent the following decade investigating how thermal energy could be stored in materials that changed phase, transitioning from solid to liquid and back, rather than simply conducting heat through walls and losing it to the outdoors. Her insight was precise. A material undergoing a phase transition absorbs or releases an enormous quantity of heat without any change in its own temperature. During that transition, the material acts as a thermal buffer, holding the space at a fixed temperature regardless of how much heat arrives from outside. In 1948, Telkes partnered with architect Eleanor Raymond to build the Dover House in Dover, Massachusetts, the first solar-heated American building to rely entirely on phase-change thermal storage rather than conventional insulation or mechanical heating. The first solar-heated American building to rely entirely on phase-change thermal storage rather than conventional insulation or mechanical heating. The Dover House used sodium sulfate decahydrate, Glauber's salt, packed into tin containers behind the south-facing walls, to absorb solar heat during the day and release it through the building overnight. The house maintained comfortable interior temperatures through the Massachusetts winter of 1948 and 1949, using no furnace, no oil, and no electricity for heating. Telkes documented the results in the Journal of Solar Energy Science and Engineering in 1952. The American construction industry filed the paper and continued installing fiberglass insulation. The specific application of microencapsulated paraffin wax to building wall panels arrived at the National Bureau of Standards, the forerunner of today's National Institute of Standards and Technology, in the early 1980s when the energy crisis had motivated federal research. The NBS team documented that paraffin wax in the C18 to C22 molecular range, with a melting point matching the human comfort temperature zone, could be microencapsulated in polymer shells and incorporated into gypsum wallboard without any change to the panel's structural properties. The resulting product installed identically to standard drywall and provided phase-change thermal storage from every wall surface simultaneously. The research was published. The product did not reach commercial production for another decade. BASF, the German chemical company, commercialized the microencapsulated paraffin technology in the 1990s under the brand name Micronal, incorporating wax microcapsules into gypsum board and plaster formulations for the European construction market. DOW Chemical developed an independent PCM panel product called Energain for the North American residential market in the early 2000s, and invested years attempting to navigate the ASHRAE compliance pathway that would allow architects to specify it in energy code calculations. In 2019, Dow discontinued the Energain product line from the North American residential market after the compliance pathway failed to materialize. The technology worked. The code table did not exist. The product died. The phase change material wall panel works through the same physics Maria Telkes applied to sodium sulfate in the Dover House in 1948, latent heat storage, delivered in a product that installs on interior walls using the same screws, tape, and joint compound as standard gypsum drywall. The panel contains billions of microscopic capsules, each between 2 and 20 micrometers in diameter, invisible to the naked eye, embedded throughout the gypsum matrix. Each capsule contains a precisely specified paraffin wax with a melting point of 22 to 24 degrees Celsius, 72 to 75 degrees Fahrenheit, the precise center of the human thermal comfort zone. When the room temperature rises above the wax melting point, the wax inside each capsule liquefies, Liquefying wax absorbs latent heat from the surrounding air, the same quantity of energy that would otherwise heat the air and trigger the thermostat. The room temperature stops rising at the wax melting point and holds there for as long as wax remains in the process of melting. No compressor runs, no refrigerant circulates, no electricity is consumed by the thermal storage process itself. The energy density advantage over conventional building materials is the critical performance distinction. Concrete stores heat through its specific heat capacity, approximately 0.88 kilojoules per kilogram per degree Celsius. To store 100 kilojoules of heat, concrete must rise in temperature by approximately 14 degrees Celsius, which means the room heats up by 14 degrees before the concrete has absorbed a meaningful quantity of heat. Paraffin wax stores heat through latent heat of fusion, approximately 200 to 220 kilojoules per kilogram at constant temperature. The same 100 kilojoules absorbed by the wax produces zero temperature rise in the room. The wax absorbs 14 times the heat of an equivalent mass of concrete without allowing the room temperature to move. That stored heat is released overnight as the wax re-solidifies when room temperature drops below the melting point, either through natural nighttime cooling, open windows, or a brief period of air conditioning running at off-peak electricity rates. The panel resets completely for the following day's heat cycle. No maintenance, no replacement interval, no consumable. A correctly specified panel maintains its phase change performance for the lifetime of the building without degradation. Columbia University's NSF-funded research at the Center for Energy Harvesting Materials and Systems documented that a 1-inch PCM wall panel installed in a 1,000 square foot home in the northeastern United States reduced summer electricity demand by approximately 50%. But does that performance hold in real homes, across real summers, in real climates outside a laboratory? The California Energy Commission's 2024 research program, the most recent and most directly applicable field study available, conducted full-scale demonstrations in 3 occupied California homes in disadvantaged communities located in Vallejo, Sacramento, and Los Angeles. Researchers installed PCM-enhanced wall assemblies and monitored cooling energy consumption, peak demand, and indoor comfort across a full cooling season. Their published results confirmed cooling energy reductions of 10 to 41% across the 3 homes and peak demand reductions of 3 to 81%. The widely varying results across 3 sites in the same state reflect the critical variable the technology's critics correctly identify: climate. Homes with larger day-to-night temperature swings achieved higher reductions because the overnight temperature drop drove complete re-solidification of the wax, fully resetting its storage capacity for the following day. The technology performs most powerfully in the climates where it is most needed: California's inland valleys, the American Southwest, the Mediterranean climate zone, and least effectively in climates where overnight temperatures remain high. The University of Washington's Molecular Engineering Building incorporated PCM wall and ceiling panels across 77,000 square feet of conditioned space, with the engineering team projecting cooling costs as much as 98% lower than equivalent conventional construction for the building's climate and occupancy profile. The projection was published in the building's design documentation and is referenced in the university's sustainability reporting. The installation is operational. The Fraunhofer Institute for Building Physics in Stuttgart, the same institution that validated wool insulation performance for the National Trust in 2003, published independent residential monitoring data in 2006 from homes completed in Germany where PCM integrated wall assemblies maintained interior temperatures 4 degrees Celsius below equivalently insulated conventional construction, under identical exterior conditions across 3 consecutive summer monitoring seasons. 4 degrees Celsius is the difference between a room requiring continuous air conditioning and a room requiring none during a typical European summer afternoon. When California recorded 50 consecutive days above 42 degrees Celsius during the summer of 2023, the longest extreme heat streak in the state's recorded history, the California Independent System Operator implemented rolling flex alerts across the grid, requesting that households voluntarily reduce electricity use during peak afternoon hours. Every household running air conditioning continuously during those peak hours contributed to the grid stress that triggered the alerts. Every household with PCM panels absorbing the afternoon heat load through phase change rather than compressor operation was delivering exactly the demand reduction the grid operator was requesting, without any occupant action, any smart thermostat, or any voluntary sacrifice of comfort. The wax was melting. The room was comfortable. The compressor was off. Every field study confirms the same cooling reduction range. Every grid stress event confirms the same demand management value. So why does fewer than 1% of American residential construction include a panel that costs $60 per sheet and installs in an afternoon? The North American Insulation Manufacturers Association represents the producers of fiberglass and mineral wool insulation in the United States. Its member companies, Owens Corning, Johns Manville, CertainTeed, and Rockwool, reported combined revenues exceeding $14 billion in 2023. Every dollar of those revenues depends on a building code compliance pathway that evaluates insulation performance through a single metric, R-value. R-value measures resistance to conductive heat transfer, how slowly heat conducts through a material from one face to the other. It was developed in the 1940s for fiberglass batting and has remained the sole compliance metric in the International Energy Conservation Code and ASHRAE Standard 90.1 for over 60 years. Phase change material panels do not perform through conductive resistance. They perform through latent heat absorption at a fixed temperature. During the hours when the wax is melting, the hours when the panel is doing the work that matters, the panel's thermal resistance is effectively infinite. No heat conducts through a material that is absorbing every arriving joule as latent heat at constant temperature. The R-value metric cannot measure this performance because R-value assumes steady-state heat flow. Phase change thermal storage is not steady-state. It is dynamic. The metric was written for a different physical mechanism. A PCM panel with documented field performance of 40% cooling reduction receives zero compliance credit in any American residential energy code because the compliance table has no column for dynamic thermal storage. Dow Chemical's decision to discontinue the Energain product line from the North American residential market in 2019 was made after years of attempting to create that compliance column. Without a code pathway, architects could not specify the product in permitted construction. Without specification, builders had no procurement mechanism. Without procurement at scale, manufacturing economics could not support the product line. The technology worked, the market structure did not. Germany's EnEV energy-saving regulation credited PCM thermal storage in residential construction as early as 2009. France incorporated PCM performance into its RT 2012 thermal regulation standard. Australia's NatHERS energy rating system includes dynamic thermal mass calculation that credits PCM performance directly. Each country wrote a compliance column for the dynamic storage mechanism alongside the static R-value column. Phase Change Energy Solutions' PureTemp product line and BASF's Micronal PCM panels are available in the United States through specialty building supply distributors. Installation requires no specialist labor, standard drywall tools, standard joint compound, standard screws. A correctly specified PCM panel installation in a 1,000 square foot home requires approximately 30 to 40 panels at a total material cost of $1,800 to $2,400. No permit is required beyond standard interior renovation approval in most American jurisdictions. No one sat in a room and decided to ban PCM, but rather, the system was never designed to accommodate it, and instead focused on the mass-produced, profitable alternative. When California's grid operator issued emergency flex alerts through 50 consecutive days of record heat in the summer of 2023 and asked 100 million residents to voluntarily reduce their electricity use during the hours that electricity was most expensive and most scarce, every home with PCM panels was already doing exactly that, automatically, passively, without instruction, without sacrifice of comfort, and without a single watt of electricity consumed by the thermal storage mechanism. The wax was melting, the room was comfortable, the alert did not reach the thermostat. The insulation industry spent $14 billion last year selling a product that measures its performance in steady-state conditions that real buildings never experience. Maria Telkes documented a wall material that holds room temperature at a fixed point during the hottest hours of any day in 1948 at the Dover House in Dover, Massachusetts. The California Energy Commission confirmed the same performance in 3 real homes in 2024. BASF has been manufacturing the microencapsulated version since the 1990s. The wax is still melting at 73 degrees. The room is still holding. The compressor is still off. The physics of latent heat have not changed since Maria Telkes packed Glauber's salt into tin containers in Dover in 1948. The question was never whether it works. The question is why we're still asking why we don't use it. This is Off the Meter. Subscribe so you never miss the next solution the world forgot to use.